All right, let's dive right in. Today, we're taking a close look at the Gemma 3 technical report, straight from Google DeepMind.
Yeah, it's a big one.
It is, especially for those of you out there, really into the AI and ML scene, researchers, engineers. This one's for you.
Absolutely. Packed with all the technical nitty-gritty.
Totally. So Gemma 3, right? It's the newest member of the Gemma family, of course. These are their open models, super efficient, and now get this multimodal.
Multimodal, yeah.
We're talking models ranging from like a cool 1 billion parameters all the way up to 27 billion. That's a
lot of parameters.
It's a lot. Okay, so for those who want the quick version, here's the rundown. Gemma 3, it now understands what it sees thanks to this special SIGLIP encoder they've got.
Very cool.
And hold on to your hats, it can handle way longer sequences of text. Like, think at least 128,000 tokens. That's because of this new attention mechanism. It's wild, really smart way of managing memory.
Yeah, the memory management is a big deal with these large models.
Huge. And guess what? It even beats Gemma 2 in a bunch of areas. Math, talking like a chatbot, following instructions, all that. Oh, and it's much better with multiple languages too.
Right.
All thanks to some seriously upgraded training methods.
They really upped their game with the training.
Big time. And the best part, for all you folks out there, all these models, they're going public.
Music to my ears. Open models.
Right. So what we're going to do today in this deep dive is really unpack the technical guts of Gemma 3. We're going to zoom in on the stuff that's truly new, groundbreaking, and what it all means, especially for the techie folks like us.
The stuff that makes us tick.
Exactly. Okay, so first things first, the architecture, big picture. Gemma 3 is sticking with the decoder-only transformer architecture. That's what the earlier Gemmas had too.
Classic, but it works.
It works. A lot of the kind of core building blocks are still there too, like remember GQA, group query attention.
Oh yeah, helps speed things up, especially with longer sequences.
Right. They're also still using post-normalization, pre-normalization with RMS norm. Helps to keep the training stable.
Essential for these big models.
Absolutely. And they've switched from soft capping to this thing called QK norm. It's a newer, more cutting-edge technique for transformer design.
Yeah, I saw that in a recent paper. It's pretty slick.
Super slick. Okay, so here's where things start to get really juicy. Gemma 3, it has some big architectural changes, evolutions, The first big one is this, it's a mouthful, but 5-to-1 interleaving of local and global attention layers. What's the deal with that?
Okay, so think about it this way. You've got the attention mechanism. Right. That's how the model figures out which parts of the input to focus on. Now, what they've done is really clever. For every 5 local self-attention layers, they stick in 1 global self-attention layer.
5 local, 1 global.
Right. And here's the kicker. Those local layers, they're only looking at a small window of the text, like a sliding window of just 124 tokens. This idea of using local attention with a limited window, Bell, Chiji, and the gang, they explored this back in 2020. Basically, it lets the model hone in on the nearby information without getting bogged down by the whole shebang.
Like a hyper-focused spotlight.
Exactly. Then you've got the global layer. This one's like taking us a step back and looking at the whole picture, the entire input. That builds on the whole global attention concept, Luong and his team, 2015.
Okay, so it's like zoom in, zoom in, zoom in, then bam, wide shot.
Perfect analogy. And they even make sure that the very first layer in the network, that's a local one. They're starting with that focused attention.
It's interesting. Why do you think that is?
My guess. It helps the model get a good grasp of the immediate context right from the start, sets the stage for the global layers later on. And this 5.1 mix, it's not random, it's all about balance. You want to handle those long sequences without blowing up the memory.
Which is a constant battle with these huge models, right? Oh, for sure.
Yeah.
So that brings us to, the whole long sequence thing. Gemma 3 can now deal with a crazy long context length, 128,000 tokens. And even the 1 billion parameter model, that one can still manage a pretty impressive 32,000. How'd they pull that off?
Positional encoding. It's all about how the model keeps track of where each word or token sits in the sequence. On the global attention layers, they cranked up the ROP base frequency, way up from the usual 10,000 to a whopping 1 million.
Whoa, that's a big jump.
It is, but they kept the original 10,000 for those local layers. So you've got this difference in how positional information is handled. Combine that with something similar to positional interpolation, like Chen and his crew described it back in 23, and it lets them stretch out the reach of those global layers.
So the global layers can see much further into the sequence.
Exactly. Without having to retrain the whole model on these super long sequences, it's a smart workaround.
Clever. Okay, so we've talked long text, but Gemma 3, it's gone multimodal. It's got vision now.
Yeah, the big upgrade.
Let's unpack that. What's the tech behind it?
They're using a 400 million parameter version of the SIGLIP encoder. Zai and Co., their paper in 23. Now, SIGLIP itself, it's a type of vision transformer that's building on Dosovitsky's work, the OG Vision Transformer paper, 2020. But the twist is, it's trained using a tweaked version of the CLIP loss. That's from Radford and his team, 2021.
So it's connecting images with text like CLIP?
Yep, exactly. These CLIP-style models, they learn to match up image embeddings with text embeddings.
Cool. And what kind of images is this encoder built to handle?
It likes its images square, 896 by 896 pixels. That's the sweet spot. And get this, they fine-tuned the same encoder with data from visual assistant tasks.
Visual assistant tasks.
Like find me a picture of a cat wearing a hat, that sort of thing.
Ah, okay, I get it. So they trained it on stuff people actually ask.
Exactly. It's all about making sure it understands the real-world questions and instructions people might throw at it.
Makes sense.
Now, another cool thing is, to make the training less resource-intensive, they share this one 400 million parameter SIGLIP encoder across all the language models. The 4 billion, the 12, the 27, and during the language model training, it's frozen. Its weights don't change.
Smart.
Yeah.
Efficient. But hold on a sec. What about real-world images? They aren't always perfect squares, right? And what about those super high-res ones? That fixed 896 by 896 input? It feels kind of limiting.
Great point. And they thought of that. They've got this neat trick up their sleeve. It's called pan and scan, or PNS for short. It's an adaptive windowing algorithm. But here's the thing. It only kicks in during inference, not during training.
During inference. Okay, so when the model is actually being used.
Right. So let's say you throw a non-square image at it, or one that's crazy high res.
Yeah.
What it does is it slices it up into these smaller, equal-sized chunks, non-overlapping crops, they call them. Each chunk gets resized to that standard 896 by 896, and then they feed it to the encoder.
Oh, so instead of squishing the whole thing, they break it down.
Smart. It helps keep all the important details and context. They don't want to lose anything by just cramming the whole image in. And it's an optimization specifically for inference. So if speed is your top priority, you can actually switch it off. Plus, they condense the output of the vision encoder down to 256 fixed size vectors. That also cuts down the computational cost of mixing the visual info into the language model.
Efficiency all around.
Totally. It's a really elegant solution to a problem that everyone doing vision stuff bumps into. Real-world images, they can be messy.
Truth. Okay, let's talk training. How do they actually teach these models? The report mentions pre-training, similar to Gemma 2, but they also use knowledge distillation. What data did they use, and how does that whole distillation thing work?
So first off, they actually used more data for Gemma 3, a little bump up from Gemma 2. The biggest model, the 27 billion parameter one, that was trained on a massive 14 trillion tokens.
14 trillion. My brain can't.
It's mind-boggling. The other models, they were trained on proportionally smaller data sets, but still enormous. This increase, part of it is because they added image data on top of the text.
Ah, right, multimodal.
And they really pumped up the volume of multilingual data, monolingual, parallel, all sorts, trying to make these models as good as they can be in all sorts of languages. They actually got some inspiration from Chung and his team, a paper from 23, on how to handle imbalances in different languages in the data.
So they made sure no language gets left behind.
Exactly. Every language deserves a fair shot.
Totally. So how do they prep the text? What tokenizer did they use?
Same one as Gemini 2.0. It's a sentence piece tokenizer, handles things like split digits, keeps the white space, and uses byte-level encodings. Kudo and Richardson, their paper back in 18, it's all in there. End up with a vocabulary size of 262,000 tokens.
262,000, wow.
And they specifically point out that it's more balanced for languages beyond just English.
Good to know. The report also talks about filtering the data. Why do they do that?
Data filtering. Super important for, responsible AI. We don't want these models learning bad stuff. So they had a whole bunch of techniques to weed out the unwanted content, the unsafe stuff. And of course, remove anything personal, anything sensitive. They also went to great lengths to clean up their evaluation data sets, make sure they weren't artificially inflated because of overlap with the training data. Oh, and they also did this cool thing called quality reweighing. Got the idea from Sakdeva and his team, their work in 24. Basically, they give less weight to data that's not as high quality.
So they're picky about their data.
They have to be. Garbage in, garbage out, right?
Right. Okay, so back to knowledge distillation.
Yeah.
Where does that fit into the whole pre-training thing?
So imagine you have a student model, right? That's Gemma 3. And then you have a teacher model, bigger, more capable. What they do is they train the student to learn from the teacher's predictions. During training, for every token in the sequence, they take a sample of the teacher's predicted probabilities for the next possible tokens. 256 of these logits, that's what they call them, the raw predictions, before they're normalized. And they weight the sampling based on how confident the teacher is about each token.
So the student is learning from the teacher's expertise.
Exactly. And the student, it tries to match this distribution of probabilities that the teacher came up with. They mainly use a cross-entropy loss function. For any of those next tokens that weren't in the sample, they basically set the teacher's probability to 0 and then renormalize the probabilities of the ones they did sample. It's a bit technical, but the bottom line is the student learns the teacher's deeper understanding of language, how words relate to each other. It's more than just predicting the next word, you know?
It's learning the nuances. Google is also releasing quantized versions of these models. What is quantization-aware training, and why does it matter?
Quantization-Aware Training, or QAT for short. It's a way to slim down the model, make it more efficient by, well, reducing the numerical precision of the weights and activations. Jacob and his crew, their 2018 paper, it's the go-to resource for QAT. So with Gemma 3, they fine-tuned the models for a short bit, around 5,000 steps, using QAT. Goal is to get the quantized model, the slimmed down one, to match the predictions of the original high precision model.
So it's like a diet version, but it still performs well.
Exactly. Still tasty, just fewer calories. They also tweaked the data they used for this fine-tuning to match both the pre-training data and the instruction tuning data, really making sure it's consistent across the board.
Thorough. What specific, lower precision formats are they offering?
They went with 3 popular options per channel in T4, where each output channel in the weights gets its own scaling factor, per block in T4, where blocks of 32 weights share a scaling factor, and switched FP8, which is a floating point format. Table 3 in the report, it's got a great side-by-side comparison, shows you the memory footprint of the original BF16 models and then these 3 quantized versions. You can really see how much memory you save with quantization, especially when you factor in the memory needed for the KV cache during inference.
Makes a big difference for running these models on less powerful devices.
Huge difference. It's all about making this technology accessible.
Okay, let's talk about the elephant in the room. Training these massive models, it takes a lot of horsepower. What kind of infrastructure did Google DeepMind use for Gemma 3?
TPUs, baby. Tensor processing units, specifically TPU v4s, v5s, and v5ps. It's all in Table 2. The setup, how many chips they used, it depended on the size of the Gemma 3 model. The Big Daddy, the 27 billion parameter one, that was trained on a whole bunch of TPU v5ps.
A whole lot of processing power.
A whole lot. And they spent a lot of time optimizing the process. For each model size, for each hardware setup, they wanted to squeeze every bit of speed out of it.
Minimize that training time, right?
Absolutely. Every second counts when you're talking about training these behemoths.
The report mentioned some cool optimizations they used. Can you walk us through some of the key ones?
Sure. So for the vision part, they did something really smart. They pre-computed the embeddings for all the images, so when they're actually training the language models, they're not dealing with the raw images anymore, just these pre-calculated numbers.
There's a ton of processing, right?
A ton. Then, to handle the sheer number of parameters and the optimizer states, they used 0-3 sharding for the optimizer state. It's like splitting up the workload across different TPU pods, crucial for not overloading any one chip. And to manage the training across all these interconnected pods, they use data replica reduction over their super-fast data center network using pathways. Barham and his team, their 22 paper, it goes into detail on that. And at the software level, it's all about the single controller paradigm from Jackson Pathways. Combined with their GSPMD partitioner and the Megascale XLA compiler, it's a whole orchestrated dance to make this distributed training work smoothly.
A lot of moving parts. Okay, after the pre-training, there's the instruction tuning. The report says they've improved their approach here. What's new?
Knowledge distillation again, but this time it's even better. They're using a larger, even more powerful instruction-tuned model as the teacher. This builds on work by folks like Agarwal and Neil, and of course the godfather of knowledge distillation, Hinton. And get this, they also added a reinforcement learning fine-tuning phase, using their internal frameworks, Bond, Warm, and Warp. Sessa and Rameh, they've got papers on those.
Reinforcement learning, huh? What were they trying to achieve with that?
They wanted to improve the model across the board, make it more helpful, more skilled at things like math, coding, reasoning, all the good stuff. And crucially, they wanted to make sure it's not going to generate harmful or offensive content. So they used all sorts of reward functions. Some were based on models that were themselves trained on human feedback. They even incorporated feedback from actually running the code that the model generated. And for math, they used ground truth rewards, checking if the model's answers were actually correct. They pulled ideas from work by DeepSeek AI and Lambert and his team.
So really throwing everything at it.
Leaving no stone unturned.
Data quality is key for instruction tuning. How did they make sure their data was top-notch?
Data curation is a big deal. They filtered out anything with personal info, anything unsafe, anything where the model was like talking about itself or revealing internal stuff. And of course, they got rid of duplicates. They also strategically added certain types of data to encourage good behavior, like they wanted the model to be better at explaining where it's getting its info from, expressing uncertainty when it's not sure, and saying no to certain questions, especially the harmful or sensitive ones.
Making sure it's a responsible AI citizen.
Exactly. It's not just about being smart, it's about being safe and ethical.
The report briefly mentions the BOS token and some formatting differences between the pre-trained and instruction-tuned models. What should people know about this? No catch.
So both types of models, they expect the input text to start with a BOS token, stands for beginning of sequence. But here's the thing, it's not the literal string BOS, it's a special token in the model's vocabulary. You gotta add it during tokenization. Like in Flax, you often have an option, add boss true. Table 4 in the report, it's got a nice visual, shows you how the conversations are formatted, with special tokens for start and end of terms. One key difference is the end of sequence token. Pre-trained models use AOS, end of sequence, but the instruction-tuned ones use end off turn. It's a small but important detail, especially if you're fine-tuning these models or building systems that interact with them.
Good to know. Okay, time for the moment of truth. How do these instruction-tuned models actually perform? They did some evaluations, both automated benchmarks and human evaluations, on the LMSYS Chatbot Arena. What were the highlights?
On LMSYS Chatbot Arena, which uses blind side-by-side comparisons with human judges, the big boy, the 27B instruction-tuned model, it scored a whopping 1338 ELO.
1338, that's impressive.
Top 10. It beat out some big names too. DeepSeek V3, the massive Llama 3, 405 billion parameters, and even Qwen 2.570B. And significantly, it blew past Gemma 2, which only scored 1220.
Big improvement.
Huge. But, gotta mention, those ELO scores back then, they didn't factor in the vision stuff, which is a whole new dimension for Gemma 3, one that many of those other models don't even have.
Right, fair point. How did Gemma 3 do on the more traditional benchmarks?
Table 6 in the report, it's got the breakdown. They compared their instruction-tuned models with Gemma 2 and Gemini 1.5 on a bunch of zero-shot benchmarks.
Zero-shot, meaning the model hasn't seen these tasks before.
Exactly. They didn't include a ton of other external models in the comparison. Results for those can be all over the place depending on how they're evaluated. But looking at their internal comparisons, Gemma 3 consistently smashed Gemma 2 across a whole range of tough tasks. MMLU Pro, that tests professional level knowledge, Live Code Bench for code generation, Bird SQL for text SQL, GPQA Diamond, complex question answering, and they encourage everyone to check out third-party leaderboards to see how it stacks up against the wider world.
Always good to get the bigger picture.
Yeah.
The report also talks about Ablation Studies. What did they learn from messing around with the architecture and the vision capabilities?
They really dug into how those design choices affect things. Figure 2 and tables 9 through 14, those are gold mines. They compare the pre-training abilities of Gemma 2 and 3 using all sorts of probes for things like science, code, factuality, multilingual stuff, reasoning, and of course, vision. Big takeaway. Gemma 3 showed clear improvements in most areas, especially in understanding and generating text in multiple languages. They do point out the risk of contamination in these probe benchmarks, though. Mirzada and his team talked about that in 24. Something to be aware of.
Makes sense. What about the local and global attention layers? What did they learn there?
Figures 3 through 6, they're all about that. Figure 3 shows that changing the ratio of local to global layers didn't really affect the overall perplexity that much. They tried 1.1, which is what Gemma 2 used, 5.1, which Gemma 3 uses, even went up to 7.1.
Interesting, so that ratio wasn't super critical.
Seems that way. Figure 4 shows they could shrink the sliding window size for local attention quite a bit without hurting performance too much.
Good news for efficiency.
Absolutely, and figures 5 and 6, these are the money shots. They show how much less memory you need for the KV cache when you use that 5.1 ratio with the 1024 token window. Compared to just using global attention everywhere, it's a big win for memory management, especially when you're dealing with long sequences.
Big win. And what about that extended context window? 128,000 tokens. How did they get that to work?
They lay it all out in Figure 7 and Table 15. They started by training the models on 32,000 token sequences. Then they scaled up to 128,000 by adjusting the rho-p positional embeddings. They used a scaling factor of 8 and bumped up the base frequency for the global attention layers specifically.
So they stretched those global layers out.
They did, and it worked. The models could handle the 128,000 context, but when they tried to go even further, things started to break down. Suggests there are limits to how far you can push this technique without coming up with new ways to handle positional info in super long sequences.
Makes sense. The report also mentions the classic question: smaller teacher or larger teacher for knowledge distillation?
Figure 8, that's where the answer lies. Short training runs, smaller teacher actually did better, but longer training runs, larger teacher took the lead. It's a bit of a trade-off. Depends on how much time and resources you've got.
Interesting. Okay. Last but not least, the Vision Encoder. Any cool insights from the Ablation Studies on that?
Tables 7, 8, and 12, those are your friends here. Table 7, it looks at the impact of image resolution during pre-training. Higher resolution, better performance downstream. Not surprising, but good to confirm.
Higher resolution, more information.
Exactly. Table 8, it highlights the gains from their pan and scan technique. Really shines when you're dealing with text and images or images with weird aspect ratios. Shows how important it is to adapt to those real-world variations. And Table 12, they compare Gemma 3 to their older multimodal model, Gemma 2. Gemma 3 actually does really well on document understanding, even beats the larger Gemma model sometimes, and it's more efficient at transferring that visual knowledge to the language model.
Efficient and powerful. Nice. Moving on to, the important stuff. Memorization and privacy. Did the report say anything about these models accidentally memorizing training data?
They did. They measured the memorization rate, how often the model spits out something verbatim from the training data. Same method they used for Gemma 2. Figure 9 shows that Gemma 3 is much less likely to memorize long-form text compared to the older models.
Good news.
Right. They also found that the memorization rate was pretty similar for the 4B, 12B, and 27B models. The little guy, the 1B, that one memorized the least.
Maybe size does matter sometimes.
They did find more cases of approximate memorization. The generated text is super close to the training data, just a few edits away. But here's the crucial part. They used Google Cloud's sensitive data protection service to scan the memorized outputs. No personal info found.
Gee, that's a relief. Okay, final big topic. Responsibility, safety, security. What did they do to make sure Gemma 3 is, a good AI citizen?
They're serious about this stuff. They keep refining their safety protocols, learning from their work on models like Gemini.
They're not messing around.
Nope. They're all about mitigating risks during training. And they do thorough evaluations, especially for the new image-to-text features.
Can you elaborate on their approach to governance and assessment?
They built on what they did for Gemma 1, but they've factored in the whole multimodal thing now. They still believe in OpenAI, sharing this tech with the world, but they're also very aware of the risks. They've got their own safety tool, Shield Gemma 2. It's a 4 billion parameter image safety classifier built on Gemma 3. And they're constantly monitoring the landscape, looking for new risks, especially with multimodal LLMs. They haven't seen widespread misuse of the Gemma models yet, but they're ready to jump on it if anything pops up. They're working with the whole AI community on this. It's a team effort.
Safety in numbers. What specific safety policies did they follow, and what do they do during training to make sure the models stick to those policies?
They align their fine-tuned Gemma 3 models with Google's safety policies. These policies cover a lot of ground. Child sexual abuse material, personal info, hate speech, dangerous activities, all the bad stuff. They filtered the pre-training data really carefully, and then they used supervised fine-tuning and RLHF, reinforcement learning from human feedback, during fine-tuning.
Guiding the model towards good behavior.
Exactly.
How did they test how well those safety measures actually worked?
Evaluations, they ran a bunch of tests, they generated all sorts of tricky queries designed to trip the model up, make it say bad things. Then they had human raters check the outputs against the safety guidelines. Gemma 3 did really well, very low violation rate.
That's reassuring.
It is. They also specifically checked how much it knew about CBRN risks. Chemical, biological, radiological, nuclear stuff. Thankfully, it didn't know much.
Good to know. So to wrap up this deep dive, what are the big takeaways for our techie audience?
Gemma 3, it's a big leap forward. Image understanding, longer sequences, better multilingual skills, stronger STEM reasoning. They designed it to be accessible, to run on regular hardware, and they put in a ton of work to make it efficient.
Lots of clever tricks.
A whole bag of tricks. The report, it's a treasure trove. Anyone who wants to really understand this stuff, or maybe even build on it, should check it out.
Couldn't agree more. And, we only scratched the surface here. For those of you who are really hungry for knowledge, go explore the full report. Go play with the models.
Have fun. It's an exciting time to be an AI.
It is. It's amazing to see how far things have come and to think about what's next.
The possibilities are endless.
Yeah. Here's a final thought for everyone. Gemma 3, it's got this amazing combination of multimodal understanding and long context processing. Where do we go from here? What kind of crazy new research and applications can we build with this? Go out there and explore. And until next time, keep on diving deep.